Payani. I'm an senior AI researcher at Cisco Research, and I'm leading responsible AI since 2021 here at Cisco Research. I want to welcome you all to our Cisco Research Summit on LLM Factuality and Hallucination. Before I start, a special thanks to Cisco TV and their technical support and broadcasting this live event to broad Cisco audience. I also wanted to thank Carla, our program manager, for all her help and hard work coordinating this event with our speaker panels and Cisco TV and making this event even possible. A special thanks to our guest speakers. Given all their busy schedule, they agreed to participate in this event, and I'm really excited to learn about their research in this topic and share them with you. One note during this presentation, there will be two multiple choice questions posted by the panel, and I'll appreciate if you kindly respond, and I'll try to present the summary of those polls at the end of the summit. So let's quickly review our agenda for today. Before I start my presentation, our head of research, Ramana, will say a few words. Following my introduction, there will be 4 talks presented by excellent panel of experts. I have had the pleasure of corresponding and collaborating closely with some of them, and I'm sure our audience will enjoy their thought-provoking and significant research work. At the end of each talk, there will be 5 minutes of Q&A. Please post any question that you may have during those talks, and I'll try my best that given the limited time, ask those questions from our speakers. If any question remains unanswered, I'll try to cover it at the end of our roundtable. So Ramana, please say a few words.
Thank you, Ali, and good morning, or maybe good early morning to some of the folks joining in. I heard that somebody from Hawaii joined, which is really, really early morning for them. But thank you so much for joining this, Factuality and Hallucination Summit. Ali has put together an amazing and distinguished set of panelists from several top universities that are actively working in this area. The field of generative AI and large language models, has, as you probably already know, it's just become super hot thanks to the release of, ChatGPT by OpenAI almost a year back. And there's been tremendous amount of interest in really harnessing the power of generative AI in various tasks like, programming, writing text, question and answers, all types of information retrieval, etc., and the list goes on. And this has become really foundational that pretty much any and every activity that we do, any piece of tech we invent, is really being reimagined with an LLM lens, and that's pretty powerful. And definitely once a generation kind of an invention that has, I would say, serious potential to really shape our digital infrastructure of the future. And I feel one of the key challenges associated with LLMs is hallucinations, as you probably are already aware. And this comes probably due to the probabilistic nature of text generation. And these LLMs generate text that may not necessarily be grounded in reality, and in other words, hallucinate. Detecting them, mitigating them, such an important and timely topic as we want to start building trust in these next generation of large language models and generative AI tech. And I really look forward to some exciting presentations, discussions, and question and answers around these topics in the summit. And thank you once again, Ali, for putting this together and moderating the panels and the talks and the question and answers and everything. And I'm really, really excited about this. Over to you.
Thank you, Ramana. I appreciate it. So let's just have a brief review of our efforts in responsible AI research here. So since we started like 3 years ago, we have funded tens of various research projects in the general area of responsible AI, topics such as diversity, ethics in AI, detection and mitigation of bias in AI, privacy and transparency and robustness in AI, we also released an open source project for data scientists with the help of our interns. It's called OpenRye, and I want everyone to encourage to take a look at it and try it. In the last year or so, and we all have witnessed how large language model has taken over the imagination of people, and both affected in industry and research. And we have shifted our focus to this area, and especially on reliability and other aspects of factuality of LLMs, and founded a lot of new research projects in top universities in this area. So just a few words on what is hallucination. So there are many different ways that people are addressing this topic of hallucination. There's no one single definition, but maybe one potentially reliable definition is basically a coherent and grammatically correct generation by these models, which is factually incorrect or nonsensical. A few notes on this topic. So training objective of LLMs does not guarantee factualness or reasoning accuracy. So this is something that we should be all aware of. The LLMs are not flawless information retrieval systems. So we don't expect that they can extract any knowledge in their training data flawlessly. That's why RAG system, retrieval augmented basically systems, has been the main first order of mitigation strategies to make these models more reliable and factfulness. The other point here is that under detection of hallucination is not an easy feat. There is no one solution to detect if a model is hallucinating. In the old days, when black white box models were available, people were looking at the probability distribution of the tokens and the generation as the measure of how reliable that generation is. But due to things like calibration error and stuff like that, and problem with the training data, that is not really an accurate metric for hallucination. So here in this, I put an example here of my interaction with ChatGPT. So a couple of weeks ago, I tried this question and I got a different answer. I asked how many letters of C are in the word spectacular, and ChatGPT back then reported 1. I asked again, and that time it fixed the issue and said there are 2 instances of the word C. 2 days ago when I did this, it didn't fix the issue. I asked it again and again, and it still insisted on 1 instance until I pointed out that there are 2 instances, and then it fixed this issue. Interestingly enough, yesterday I repeated this experiment, and this time it used a different approach, and it used a Python tool. So converted the problem into a Python code and gave me the correct answer. So this is a good news. In a way, it shows that tools can help us make these LLMs more factual, more reliable. The issue, however, is not fully fixed for 2 reasons. First is that these conversion from the natural language to a formal, basically a presentation like a Python code or logic representation is not flawless. There are mistakes in this conversion. The other part is that the language model can still hallucinate. So after this correct generation, I tried to challenge ChatGPT 2 times, and the second time I did this, it changed its response and it said, upon closer inspection, it's clear that the letter C actually appears only once in the spectacular, and that's very interesting to observe. So we have looked at this topic of hallucination and factuality in LLM broadly. In general, we have looked at 3 different areas. The first series of work that we have looked at and funded are about training and fine-tuning. The main idea here is that if we start from better data, more clean data, more factual data, or more representative data by a specific set of core set selection, we can have more factual LLMs. And that has been shown in research, basically, that is true. It's not completely fixed the issue, but it helps, definitely. The other approach here is that we can specifically design data set to improve certain skills. For example, we can generate a data set for logical reasoning. And it has been shown that that type of fine-tuning can improve the correctness and logical consistency of these models. In the detection part, as I mentioned, there are some white box approaches based on the probability distribution of generation, but most of the effort has been on black box, basically, approach with the abundance of use of ChatGPT and other basically proprietary models. And there are many different approaches based on like fact checking, based on knowledge graph, based on self-reflection, consistency, and a lot of new development are happening here to detect if the generation of a language model is reliable. These are per sample, basically per instance of inference. There is also a series of work that look at the benchmarking of language models to assess the general capability of these models in certain area. And we have done some work in this area ourselves and also funded a couple of works. In terms of mitigation, our main goal here is to improve the factuality and reasoning capability of language models. The first series of works were based on basically creating a trajectory of outputs that leads to a better reasoning, like a chain of thought and its variation, which basically expand the search space of finding the right solution, like a tree of thought, a program of thought, or graph of thought. There are other approaches based on formal representation. We can convert the problem, as you see in the Python example, into some formal language. So either a programming language like Python, or like a first order logic, or some other form of formal representation, and use external tools to improve the reasoning and factuality. There's also the planning part, and this is specifically important when the problem is not simple. If the problem requires multiple different parts, we need to actually plan and separately solve different parts of a problem until we get the final result. There's a series of agent-based approaches as well, which I don't have time to go over right now. So last part of my own presentation, very quickly, I will review some of the works that we did here in this space ourselves, in-house research. And we have done some work on formal logic reasoning, which I don't have time right now. This work that I'm right now presenting here is about temporal reasoning. So we did a work with our intern that I'm going to present next month in AAAI about prediction over knowledge graph. It's a formal, basically temporal knowledge graph reasoning using logic programming. Here, we try to extend this to LLM and try to understand how skillful are LLM in answering questions involving temporal aspects of events, basically order of events and different aspects of the overlap, time lapse, and different things that involve time. And interestingly enough, even though the questions that we generated in our synthetic dataset were quite simple, out of the box, GPT-3 and GPT-4 were not really able to fully address this problem, and in most cases, like the accuracy is below what we expect, like 0.7 or 0.6. And we have devised some new ways of addressing this problem. I don't have really the right time to go over this. Hopefully in our next tech talk in a month, I will go over this project in more details. So we don't have more time now, so we can now start introducing our first speaker. Our first speaker is William Wang. He's a professor of artificial intelligence at UC Santa Barbara. The topic of his talk is Principles of Reasoning, Compositional and Collaborative Generative AI. I invite our guest speaker to start. Thank you.
Thank you very much, Ali, for the kind presentation. This is my great honor to be visiting the Cisco Summit. And today I'll be talking about our recent work on compositional and modular generative AI design. And like Ali said, I think this is super exciting area to focus right now. And in today's talk, I will talk about 3 things, but I think mostly I just have time for 2, so I'll focus on 2 key aspects of generative AI. The main thing I want to mention is the science of large language model. So when I talk about the science of LLM, people got confused and thought that I'm talking about looking at large language model for science. But here what I'm saying is that a lot of the AI developments are based on scaling, right? More data, more compute, and more parameters. Right now, there's a lot of questions about how these models hallucinate, right? How these models actually, come up with these emerging abilities. So I think now is a very exciting time to look at the science of large language model by analyzing the theories for these large language models and see how the theories can inspire us to design better algorithms. So that's the first part. And the second part about the work that I'll describe is very deeply connected to the theme of today's summit, that is hallucination, right? So how do we reduce hallucination? I think a year ago, people were saying, well, maybe we just need to scale up. Maybe we go from GPT-3 to GPT-4 and we have, more data, more parameters, more compute will solve the problem, but it is not the case, right? So fundamentally, how do we actually teach language models to do better? So I think looking at this direction of neurosymbolic reasoning would be very critical to build modular AI systems that we can reduce hallucination by better design. And if we still have time, I can go to the third part. I'll tell you a little bit about how to apply the algorithms of in-context learning in reducing hallucination for other generative AI techniques. Okay, so let's just dive right in. This first part is joint work with my PhD students, Xingyi Wang and Wanrong Zhu. So this was actually recently presented at NeurIPS a month ago. All right, so emerging ability of large language model. I think people are now very familiar with all these amazing abilities. This is a paper from Jason Wei from 2022. Basically, they show you can increase the compute and suddenly, large language model would be magical and they would be able to solve some of the very difficult tasks. So for example, if you look at the first one, this is not, simple arithmetic task. This is modified arithmetic. So in the past, you would say, well, can we teach machines to learn addition, subtraction? Those would be very easy, but they're redefining addition. For example, 200 plus 1 used to be 201, but they redefined the operation so that 200 plus 1 is 202, right? So this is very difficult, right? So how would you be able to teach machines to understand the new definitions for this different, tasks? So it turned out, like I said, the model gets better, the system are, magically able to learn this challenging task. People have no idea, right? So why the models have this ability? For example, in-context learning is also an ability I will just describe in the next slide. So for the first part of the talk, I hope we'll, discuss a little bit more about in-context learning and how exactly we can understand better about in-context learning. So this actually affects the later part of the talk, how we actually design tools using in-context learning to reduce hallucination. Okay, so what exactly is in-context learning? Well, it's actually very simple because in the past for machine learning, the paradigm is more like, okay, you have the data. So I take your data, I train a model from scratch. Now I deploy the model and customers and users can use it for inference. But the paradigm has already changed in the sense that nobody actually training from scratch, right? So we're taking these pre-trained large language models and we're giving demonstrations to these large language models And these demonstrations are just a few of them, right? So it's not like a huge amount of data. So in this case, the question becomes, how do you select, right, this demonstration? A simple example would be translating from French to English. So you would basically choose 3 examples of French to English, and then you have a new French word, right? You're trying to see now whether the system can translate this French word or French sentence into an English sentence. So how do you choose the demonstration? How do you choose the examples? There has been studies in the last 2 years focusing on selecting similar examples. So this is very good strategy, because you can imagine that if you choose a demonstration or examples similar to the French sentence you're trying to translate, potentially this would give you a very good result, right? Because you're doing a retrieval-based approach, you're finding the most similar sentence and you're doing translation. Yes, this does give you a very good result. But a big part of this is that most people don't really understand how these large language models like ChatGPT or GPT-4 they are able to do this kind of in-context learning, meaning that, French to English may be very easy, but if you try something very difficult, for example, Tibetan language or Manchurian language, those very rare languages, the system can still somehow do it. So how does it actually have this capability to do this unseen task or difficult task? There has been theories studying what's exactly is going on. For example, Stanford has this paper looking at hidden Markov model, trying to see what's going on. And there's people looking at, maybe, large language models is mimicking gradient descent in the inference time. So there has been a lot of, discussions why the language model can solve so many different tasks, including tasks that it has not seen before. Okay. So in our lab, we've been thinking from the latent variable perspective, because for large language model, typically, the only thing you need to remember is that it's basically taking the prior context and predict the next token, right? That's the training for large language model. But this reminds us there is some prior work in this area from a while back based on topic modeling. And from the topic modeling, we're trying to understand what are the topics, right, associated with various of documents. So it's inferring a distribution of topics, and for each topic, there are words associated with each topic. So this gives us some inspirations. So maybe we can study, right, this kind of, large language models from the lenses of latent variable models. And the idea is that we're looking at the probability output by a large language model, and we can say, how do we get the answer, right? So the probability of getting the answer is conditioned on what you write, right, as the prompt, right? So the prompt is very critical here. So for example, what are the English and French pairs that you've chosen? What is the task description? This is the prompt. So given the prompt you've written, how do we, estimate the generated continuation? So from our work, we are decomposing the generation into 2 parts. One part is that we hypothesize that maybe the system is trying to infer a latent representation of the tasks that you're trying to solve. So the task here is represented by theta, which is the latent variable. So based on theta, how do you generate, right, this continuation? But of course, given the prompt you've written, you've wrote something, there's English examples and French examples. So in this case, the system is trying to figure out what exactly is the task you're trying to solve. Maybe you want to solve machine translation, right? Going from French to English. So that's our hypothesis. And because we have this Bayesian interpretable ways for in-context learning, we can also break down the prompt and answer paradigm into an in-context learning paradigm by breaking down the prompt into a K-shot demonstration and also your test example, right? And still, we can use this decomposition to decompose the answering part for the language model into 2 components. One component is that based on the inferred task, is automatically completing, right, the answer. And of course, given your demonstration, how does the system actually trying to figure out what tasks that you are trying to solve? But here we have some data generation process, because you know, there are different ways, different directions you can assuming the generation direction. So here we're assuming that based on the prompt, based on the inferred latent variable, that the system is trying to generate the answer for you. So theta here, you can think about it as a high dimensional vector that is, you know, capturing, you know, the definition, right, for the task that you're trying to solve. And assuming, right, that we're able to infer the latent variable theta, then the really nice thing about this formulation is that, you know, the probability of generating the answer given the inferred task and the prompt, this is the Bayesian optimal classifier, right? So this would be very ideal for the solving this problem. Okay, now here's the question. We have a little bit of theory about, you know, Bayesian interpretation of in-context learning. The question is there any actual algorithm, right, that can be developed to improve the in-context learning paradigm? So the answer is yes. So now we can decompose the in-context learning into two parts. One part is very similar to soft prompt tuning. So we're learning the latent concept representation for each task, right? That's the first part. And given a learned classifier, given the, you know, the soft prompt tuned classifier, now we can actually select the demonstration, right? You can select better examples to solve your problem. And there's also a theoretical guarantee that the in-context learning classifier is also a Bayesian optimal classifier if you infer, right, the theta correctly. Okay, so how does it look? Well, it looks very complicated, but the actual algorithm is relatively simple, right? So like I said, there are two parts. The first part is that given the task you have, then we create some tokens, right? The latent tokens into the vocabulary, and you're learning, right, this latent representation of these additional tokens to optimize your particular task. For example, classification, right? You still optimize for the cross entropy loss. And then the second step is that given this classifier you've selected, the next thing is that we can basically choose the best optimal in-context learning examples, right, based on the classifier you learned. Now, the final thing is that there's, you know, GPT-3, there's GPT-4. It's very difficult to fine-tune them. You don't have to fine-tune them anymore. You use the selected examples and you feed them to GPT-4 or these gigantic models and see, right, by choosing this carefully selected in-context learning examples, does that improve, right, the performance for in-context learning for these gigantic models? So this is the empirical result we got. So we've been experimenting with various of different type of autoregressive large language models going from GPT-2 to GPT-3. We've been looking at 8 classification problems and run each example by 5 times. And here, the green bars, these are the uniformly sampled random examples as, you know, the English-French pairs for your problem that give you the worst performance for the task. But if you do RAG, if you do retrieval augmented approach, that you are trying to select the most similar examples from the retrieval time, and that gives you the blue bar. These are the second best results. But our approach uniformly gave you the best results over various of type of different versions of GPT models. And what's interesting about this paradigm is that, you know, you don't have to do fine tuning, right, with GPT-3 or GPT-4 because it's so expensive. It's not very feasible. There may not be API for fine tuning GPT-4, right? That I'm not sure. But the nice thing is that you can use our approach to learn the latent concept variable for the smaller models like GPT-2 large and use the selected demonstration for bigger models like GPT-3 and GPT-4. And that actually still gives you improvement using this approach. So you can see how this actually transferred from the smaller models to the big models for in-context learning. So there are a few observations for this part. First of all, we hypothesize there may be a latent concept, or latent task variable inference procedure for in-context learning, so that the system is actively inferring, right, the task you're trying to solve, and by decomposition, by doing the decomposition, we're able to select pattern demonstrations, and this can be transferred across different tasks to improve in-context learning. So this is the first part of the presentation. Okay, so the second part is also super exciting because now we know a little bit about theory and potential interpretation of in-context learning. How do we use in-context learning to solve difficult problems, like Ali mentioned, for example, hallucination? So this is our work on logic LM by trying to improve the reasoning process and solve difficult logical problems using symbolic solvers. This is joint work with my postdoc Liangming Pan, PhD student Alon Albalak, and Xingyi Wang. This was published at MNLP, also presented last month at Singapore. So the fun thing about this work is that immediately after we published this work on arXiv, OpenAI and Google DeepMind, they both contacted us. So it turned out that actually they are doing very similar things and trying to fundamentally build neurosymbolic systems, trying to improve the face-and-witness issue. Okay, so that said, why do we have to do this kind of neurosymbolic system? Well, we think about natural language reasoning. That's what everybody's doing, trying to use GPT-4 to solve all these different problems, regardless of the nature of this problem, right? Some of the problems require more precise solutions. Some of them are okay, like creative writing, you don't have to be precise. But if a problem requires a precise solution, sometimes using natural language only to do reasoning will give you a lot of errors. Okay, so this is a big problem. For example, solving logical reasoning, solving problems, you want to have a constraint. For example, if we want to determine the presentation schedule of today's presentation, there may be constraints about what people present. It's very difficult to do that kind of planning, right, with a large language model. So everybody still does that by hand right now. So what we are saying is that if we are able to translate the natural language problem description into a formal or symbolic reasoning representation, then we can use some external tool, for example, symbolic solvers, to execute this logical reasoning rules and programs. So that gives you some guarantee, right, about the output in terms of quality, in terms of reducing hallucination. And if we think about the pros and cons, in general, natural language is very flexible, right? That's why everybody likes to use large language models. But like Ali said, in many cases, they're not very reliable. So if you have critical problems, you want a precise answer, usually they're not very reliable, and they, you cannot easily verify their output. Whereas for the formalized symbolic reasoning, it's not very flexible, but it's highly reliable and is verifiable. So the question I'm asking in this work is that, is it possible to combine both formalisms so that we have the best of the both worlds? So the answer is yes, there could be actually a collaboration between large language models and symbolic solvers. The idea is to translate the problem into the local grounding of the problem in the formal language, and then we can call this various of different external tools to solve, so for example, logical reasoning or constraint reasoning problems. And then we can learn from feedback. We can do more iterations. If there's a translation error, the program doesn't run, that's okay. We learn actually from the compilation errors. We learn from the feedback from these different tools and teach language models to revise their translation until we can run the system. So for logic LM, like I said, it's not very complicated. It's based on in-context learning that I just described. And the idea is that we can describe the formalism, can describe the problem using a template. And based on the template, based on the query, the large language model can translate, right, this into different rules, and then we execute external, for example, constraint satisfaction tools. And finally, the external tool will tell us whether it's true or false. If there's syntactic or symbolic errors, then we can do self-refine and continue to refine the inference process. So for logic LLM, we tested on various of different kinds of reasoning data sets. For example, deductive reasoning, first order logic, there's a constraint satisfaction ones. We look at different symbolic solvers to look at different problems. And like I said, the solution is based on in-context learning. So take some examples. There are some in-context exemplars, and then we send them to a large language model, and we're looking at the output as the learned rules from these large language models. And then we execute these rules using external solvers. So there are a couple of challenges. One challenge is that, of course, translation, right? So translation is still challenging, but using in-context learning, it is really fast. It does not require additional training. So this is really nice. So LLMs are really good at translating natural language into formal programs, for example, SQL or Python, and so on and so forth. The other thing, like Ali mentioned, this work is also related to tool-augmented LLM. So even though we're focusing on reasoning and logical reasoning, but certainly, how do you choose the right logical solvers for the problem? This is deeply connected, to tool-augmented large language model. But the empirical result, I would say, is very promising. So we've been looking at GPT 3.5 and GPT-4. In general, on this very challenging data sets, you can see with the standard prompting approach, for example, on AR-LSAT data set, the accuracy is only 33%. With the chain of thought reasoning Ali mentioned is about 35. Using logic LLM, we're able to get to 43% accuracy, which is still very low, but this is still in the early phase, but it's much better than the prior state-of-the-art approach. Another thing that is quite interesting is that you can see many of the problems that GPT-4 cannot solve require multiple steps in the reasoning process. And when you have 5 reasoning steps, you can see the standard prompting approach and the chain of reasoning approach, chain of thought approach, their accuracy actually drops significantly because you're using natural language. So you have an accuracy issue with one step, and this would multiply, right? And then you will have really, really low accuracy at the end. So for example, for chain of thought, you started with 70% accuracy, but when you get to the 5th step, the accuracy already dropped to 50%. Whereas for logic LLM, we can stay above 70%, even if this is 5 step and it's relatively difficult problem to solve. Okay, so what exactly are these problems, right? Like, why are these problems difficult to solve? I'll give you one example from the LSAT data set. So this is the law school entrance exam, many people know. And, this is a standard task of, we need to organize presenters and their schedule, very similar to our summit today. So there are 3 speakers. Each person has their expertise. They talk about different things. So how do you arrange the schedule? Well, it's not very easy because there's a lot of constraints. For example, the second speaker, they cannot give 2 presentations in a row. And for particular topics, it might need to be given earlier, right, than some other topics. And there's a various of constraints that is very practical. So if you just input this to GPT-4 or ChatGPT, it gives you about 30% accuracy. But if you use a neurosymbolic solution, connecting natural language together with logical solvers, this could give you significant boost in getting better performance. And of course, choosing the right formulation is important. If you choose the correct formulation, you get good result. If you choose the wrong language, wrong formulation, you can still get the wrong result. So it's not, super easy that you can use Python to solve all of the problem. it is not the case, right? So there's still a lot of work needs to be done in this area. So like I said, there are two challenges. One is to correctly translate the program into local grounding such that your external solver will be able to solve it. This is still challenging. The second aspect is to, like I said, decide what reasoning system that you should be using to solve it. That is still not solved. Okay, so in my last two slides, I want to mention that this approach is very general. You don't have to use it to solve natural language only problems. Here we're looking at generative AI, text to image, right? We found out that you can use logic AI, logic LLM-based approaches to improve the text to image kind of generative AI systems by translating the query into the CSS language to generate a layout. And based on the layout, you generate a 3D design or generate an image. These kind of results would be more faithful, right, to users' input. So we also show that in the vision domain, this is really the case. Okay, so to conclude today's presentation, there are two things I mentioned. One is that I call for more principled algorithm designs and theories and analysis to help us to understand hallucination, to help us to understand the emerging capabilities of large language models. And we demonstrate a latent variable theory and show how to build better algorithms for in-context learning. Okay, the second part of the presentation I showed you is that many of the state-of-the-art AI systems are actually modular AI systems, and we need to improve the systems to deal with challenging problems like logical reasoning, like generative AI, and we show that logic LLM is a critical solution that can improve the quality of the outcome, and it can improve a lot of the hallucination we mentioned. So this concludes my presentation. I believe I still have 3 minutes for questions. Happy to take any questions. Thank you very much.
Thanks, William. Great thought. I really enjoyed the discussion. Just a few questions here that I'll have. Let me see if I have questions from the audience as well. Okay, so the first question is, so in the first part of your talk, you discussed the in-context learning and an algorithm for selecting an optimal, basically, example for the in-context learning. How does this compare to some other works that use, like, for instance, reinforcement learning for the same, basically, goal for selecting the best subset of example for in-context learning? And more, in addition, does it require some form of like do you require training using labeled data for the soft prompt tuning of the first part of this approach?
Yeah, so this is an excellent question. So our lab actually started looking at reinforcement learning for NLP back into 2017, 2018. And we were looking at RL for knowledge graph reasoning at the time. And we also actually tried RL for selecting examples. The challenge with RL for selecting example is that it's very difficult to form a Markov chain because the states are not really related with each other, right? The examples, they are very independent, right? And sometimes many data sets have this IID kind of assumption, so that in RL, when you condition on a state and you take an action to select an example, the relationship among different examples are not actually very strong. So that using RL for selecting in-context examples become very unstable in the training part and doesn't really help us much in this particular case. So that's why we actually did not do RL. We went with soft prompt tuning, which is more like supervised learning, right? Supervised fine tuning. And this way we can actually learn the latent variable representation directly so that the learning efficiency is better, and then we can directly infer the latent variable and select better examples.
Yeah, that's very interesting. I'll look forward to reading that work. And I have some other questions, but for the lack of time, I'll ask them in the round table. Thank you very much, William. So
thank you.
And now it's time for our second talk here, presented by Kai Xu. Kai is assistant professor in Department of Computer Science of Illinois Institute of Technology. The topic of his talk is combating misinformation in the age of large language models. Thank you. Hi, Kai. Please start.
Let me unmute myself.
Yes, you can share now. Thank you.
Okay, good. 1 second. Okay, can you see the screen?
Yes.
Okay, great. Thank you, Ali, for the kind introduction. And it is my great pleasure and honor to share my research about combating misinformation in the age of large language models. I will be happy to take questions at the end of the talk. Okay, so let's get started. I will first introduce the background of misinformation in the age of LLMs, and then dive into the research on combating misinformation and talk about my future research plan. Okay, so misinformation and disinformation have led to a new world disorder with severe consequences and for the society and economy. Basically, we're now living in the age of disinformation age, right? And disinformation usually refers to the false information that is intentionally spread, and actually social media platforms play an important role in accelerating the information dissemination. According to a post published in 2019, the epidemic of online fake news, which is a typical example of disinformation, have cost the global economy around $78 billion. So we can see that the threats of mis and disinformation to democracy, public trust, online safety, and journalism need urgent action. So it is quite important to study misinformation in this digital age. However, it is not easy. We are facing several challenges, and combating misinformation is a daunting task. We have several dimensions of challenges. First one is from the technology point of view, the ability of AI technologies such as LLMs to generate misinformation may surpass those techniques to identify the information. And it is basically an arms race environment. Second, social media platforms, their incentives are not always prioritized to contain or mislead or mitigate misinformation. In some aspects, their incentives are aligned with spreading more of misinformation. And third, from human psychology perspective, we are very vulnerable to misinformation in the process of consuming and processing information. And research shows that a false story may spread 6 times faster than a factual story online. So there is a pressing need for developing a holistic framework to address the aforementioned challenges to ensure better misinformation detection, intervention, and attribution. Okay. So what has been done already, you may ask? So in this slide, we provide an overview of the landscape of representative tasks or problems in combating misinformation, mainly including the following 3 tasks: detection, intervention, and attribution. The goal of detection is to detect the veracity of the text. And intervention approaches go beyond the algorithmic solutions and try to mitigate the effect and mitigation, the spreading of misinformation. Attribution approaches aim to trace back and find out the sources of misinformation. And it is crucial to implement these strategies in an interdisciplinary manner and address the complex challenge of misinformation. So recently, we can see that large language models have a powerful performance in many applications and have made a transformative impact to the society. And typically, ChatGPT and GPT-4 have shown its powerful performance in understanding human instructions, generating fluent language, and performing various tasks. Then you may ask, what is the difference between LLMs and conventional pre-trained language models? Well, the main difference, I think, is the scale of the parameters. As you may see in this example, small models with 8 billion parameters may perform very well in tasks like language understanding and question answering, while larger models with 62 billion parameters can perform on a wider range of tasks, right, such as translation, summarization, and so on. Even bigger models with 540 billion parameters enables the model to tackle a wider range of tasks, including reasoning, comprehension, semantic parsing, and even understanding human jokes. Okay. So what will happen when LLMs meet misinformation? Actually, LLMs can be a double-edged sword in the fight against misinformation. Why? On the one hand, we want to ask, can LLMs detect misinformation and provide explanations? For example, in this case, we can ask ChatGPT to determine whether this misinformation is misinformation or not. Vaccinations contain dangerous toxins like mercury and alumina that are harmful to our bodies. ChatGPT can actually accurately point out it is misleading and contains misinformation, and even provide a very concise explanation for this decision. And even though this is relatively hard for a normal person to identify because it contains terminologies like mercury and alumina, which are medical terms. However, on the other hand, it's important to note that LLMs can also generate misinformation. First, because LLMs cannot get access to up-to-date information, and due to its inherent generation strategies, it may lead to hallucination, and it will eventually generate misinformation unintentionally. For example, we can ask ChatGPT to write a piece of short news, and it will generate the text that containing hallucinating information such as names, date, and address. Second, LLMs can also be possibly used by malicious users to generate misinformation intentionally. For example, ChatGPT is prompted to generate a piece of misinformation, and it will generate information like eating apple seeds can cure all type of cancer. Okay? It's obviously a piece of misinformation. So essentially, we are facing both opportunities and challenges when combating misinformation in the age of LLMs. On the one hand, LLMs can potentially be utilized to detect misinformation by leveraging their intrinsic abilities and augmented abilities. The intrinsic abilities include its significant amount of word knowledge and the strong reasoning abilities, especially in the zero-shot or few-shot way. And the augmented abilities include such as retrieval augmentation, tool use, and multimodality, and even agent mentioned by Ali and other speakers as well. On the other hand, one important challenge is to detect LLM generating misinformation, which can be unintentional and intentional. So unintentional generation refers to misinformation created by LLMs due to the inherent hallucinations. On the other hand, intentional generation may involve LLMs purposefully generating misinformation with malicious prompts and eventually lead to fake news, rumors, clickbait, propaganda, and so on. So next, I will introduce two of our recent work attempting to investigate both opportunities and the challenges when combating misinformation in the age of LLMs. And we are interested in the following two questions. The first question is how LLMs can help detect misinformation, and can LLM generated misinformation be detected? I will first introduce the work that recently published at EMLP 2023 on explainable claim verification via knowledge-grounded reasoning with large language models. So due to the spread of large amount of misinformation, automated fact-checking becomes increasingly important. And a typical pipeline for fact-checking usually involves the following steps. The first step is to identify those check-worthy claims using claim detection. Next, it will retrieve the evidence and document to check against the claim. Finally, it will make the verdict prediction and provide justification. Through these steps, it will provide the final prediction of the claim to identify it's false or not and provide justification in natural language. So although this pipeline has shown great results with techniques such as reasoning over claim evidence graph, the reliance on annotated dataset is still a big challenge. Now, in the age of LLMs, we can see several advantages of using LLMs for fact-checking compared to pre-LLM methods. The first advantage is there's no requirement for annotated training data, which is usually expensive to create and usually domain-specific. Second, this zero-shot and few-shot fact-checking becomes possible with LLMs, which is more practical in the real-world scenario. And lastly, the LLM's ability to generate high-quality text can produce justification of its decision in natural language. While all of these advantages may seem too good to be true, right? We do need to solve several challenges to do fact-checking with LLMs. The first challenge is the internal knowledge of LLMs are not always correct or up-to-date, right? So to address this, we can use knowledge grounding, meaning that we can retrieve knowledge from external trusted sources. Another challenge is LLMs do not perform well on reasoning-intensive tasks, okay? And we can use low-level symbolic forms, such as first-order logic, to guide LLMs to perform reasoning-intensive tasks. And LLMs can hallucinate when producing justifications. So we propose to integrate the knowledge grounding and the accurate claim decomposition to obtain more accurate justifications. I will introduce more details in the next few slides. So we propose this framework called FOLK, meaning first-order logic guided knowledge grounded reasoning. Essentially, giving the claim regardless of its domain or types. FOLK first use first-order logic, or FOL, to decompose the original claim into a subset of claims. And we can use this subset of claims to generate follow-up questions to get the knowledge grounded answers. So after we have this subset of claims, then we can retrieve the knowledge grounded answers from external sources by using the follow-up questions. And at the end, we can perform a veracity prediction and explanation generation and produce the prediction result, whether it's refuted or supported, and provide a very concise explanations. Specifically, first, why we want to perform FOL-guided reasoning? Because existing work have shown that LLM's performance on complex reasoning tasks may not perform very well when reasoning directly on text. And there are many research showing that LLMs can better understand text by converting the textual input into symbolic languages. So as you can see from this example on the right, essentially what we do is giving a claim on LK won a silver medal in the 2012 Sport Accord World Mind Games inaugurated in July 2011 in Beijing. So we first use first-order logic to generate two predicates. Each of the predicates is corresponding to a subset of the claim. For example, the first predicate is to verify whether LK won a silver medal. And the second predicate is to verify whether this game was inaugurated in July 2011 in Beijing. Based on these two predicates, we will generate two follow-up questions. So the first follow-up question is, what did LK win in the 2012 Sport Accord World Mind Games? And the second question is, when and where was the 2012 Sport Accord World Mind Games inaugurated? So this is our first step. The second step is we'll do knowledge grounding, because as I mentioned earlier, LLM's knowledge may not always accurate. So we retrieve the knowledge grounded answers using external sources such as Google search or Wikipedia. And basically, in the earlier example, after we have these two questions, we can then obtain the knowledge grounded answers, and we can have the response, such as in 2012, he won the silver medal. And for the second question, we can know the information that this game was inaugurated in December 2011. So the last step is to perform the veracity prediction and explanation generation. And the idea is to empower a meta-reasoning over the FOL-guided follow-up questions and their knowledge-grounded answers. So again, in the earlier example, folk makes the veracity prediction and produce explanations. And eventually, it can accurately identify that the first predicate is true and the second predicate is false, and even provide a good explanation to show that this claim was false because it was inaugurated in December 2011, not July 2011. So this basically is how our framework is working. So our main experiment results show that folk can outperform existing methods on many existing fact-checking tasks, including multi-hop reasoning and numerical reasoning and so on. So essentially, we show that the proposed model can achieve a superior performance in claim verification. And it's important to note that folk can be more effective, especially on those complex reasoning tasks in many, many cases. Okay. Additionally, we show the importance of the FOL guidance and knowledge grounding separately. First, we compare the reasoning strategies with the same follow-up questions generated by folk. The idea is to compare whether different types of reasoning can make difference with the same questions. And from this table, we show that the FOL-guided reasoning is more effective than chain of thoughts and the self-ask reasoning. In addition, we evaluate whether the knowledge grounding really helps, comparing to the LLM's internal knowledge. So from this figure, we show that the folk with knowledge grounding can perform better than LLM's internal knowledge to answer those questions. In addition to improving the detection performance, we also evaluate the quality of explanations generated by different methods in terms of coverage, soundness, and readability. So to measure these metrics, we ask human evaluators to rank all those measures and measure the mean average ranks. And then from this table, we can see that folk can actually generate more informative, accurate explanations with great readability. Okay, so to summarize our first piece of work, so folk have addressed two major challenges: the scarcity of annotated data and the absence of explanations. And folk demonstrate promising performance on various challenging datasets with only few in-context learning examples provided. And folk actually is a very scalable framework, can work very well on smaller LLMs and larger LLMs in many cases. Okay. So now we have shown that LLMs can help detect misinformation. Next, I will introduce whether it is possible to detect LLM-generated misinformation and how. So this paper was recently accepted at ICLR 2024. So LLMs generating misinformation is already a serious threat, and there are many posts reporting about these alarming risks in various domains. For example, in journalism, it has been found that a large number of AI-generated news websites out there, and it obviously pollutes the online information space. And in finance, it is reported that AI-generated misinformation is becoming the biggest threats to the global economy. And in politics, it's reported that ChatGPT can potentially be utilized for misinformation campaign and generate propaganda, which is threatening the foundations of our democracy. And in healthcare, it's reported that many AI-generated books started to occur in platforms such as Amazon and may cause life-threatening consequences. So in order to combat LLM generating misinformation, we need to understand the difference between human written and LLM generating misinformation. Okay, so conventional misinformation is manually written by human directly. However, in the age of LLMs, human can just need to design better prompts, and the LLMs can generate a piece of complete misinformation. So a key question we want to answer is LLM generating misinformation more difficult to detect compared with human written misinformation? We can decompose the problem into three specific research questions. The first question is, how can LLMs be utilized to generate misinformation? And can humans detect LLM generating misinformation? And can detectors detect LLM generating misinformation? So to answer the first question, we propose to categorize or taxonomize the LLM generating misinformation from 5 dimensions, including types, domains, errors, sources, and intents. For the types, domains, and errors, we can generally follow the categorization of human written misinformation. As for the sources, we propose to categorize the LLM generated misinformation into hallucination, arbitrary generation, and controllable generation, which we'll introduce in detail in the next slide. As for the intent, LLM generated misinformation can be unintentional or intentionally generated. So we propose to categorize the potential methods to generate misinformation with the following 3 types. The first type is hallucination generation. An example is we can ask large language models to write a piece of news, and LLMs will probably generate text containing factual errors, especially for those very fine-grained information such as date, names, and so on. And the key reason that LLMs cannot get access to up-to-date information and its intrinsic process of generation needed to hallucination. The second type is we call arbitrary misinformation generation. And example prompts like, please write a piece of misinformation. And it will generate a content with arbitrarily misinformation message. And we can also add some constraints, say the domain should be in healthcare, and the type should be fake news. So we can then generate those misleading information with certain domains and types. And the third type is we call controllable misinformation generation, using paraphrasing, rewriting, open-ended generation, or even information manipulation. And such strategies can either convert existing factual information to misinformation or make existing misinformation more deceptive and undetectable. Okay. So now we have our first finding. Basically, LLMs can follow users' instructions to generate misinformation in different types, domains, and errors. We now aim to answer the second question: can humans detect LLM generated misinformation? So we compare human detection performance on both LLM generated and human written misinformation with the same semantics. And this is the result. So from this table, we observe that in most cases, human evaluators, they have lower successful rate in identifying LLM generated misinformation compared to human written misinformation, indicated by this red color here. So our second finding is LLM generated misinformation can be harder for humans to detect than human written misinformation with the same semantics. We now move to our third question: can detectors effectively detect LLM generated misinformation? So in this figure, x-axis are different generation approaches, and the y-axis is the successful rate. So we can see that it's generally hard for detectors to detect LLM generated misinformation. And interestingly, GPT-4 has shown powerful results and even surpass the human performance. But human performance can perform better than ChatGPT in this case. So after evaluating the overall performance of LLM detectors, we further investigate whether or not LLM-generated misinformation can be harder to detect compared to human-written misinformation. Again, our main message here is that LLM-generated misinformation can be harder for misinformation detectors to detect than human-written misinformation with the same semantics. Okay.
Just a reminder that we have 5 minutes left.
Yes, I have just 3 slides, so at least we're good. Yeah, so basically to summarize, we have, based on these findings, we can derive several important implications on combating LLM-generated misinformation. The first one is LLM-generated misinformation can be more deceptive and potentially cause more harm. Okay. Second, there's a potential major paradigm shift of misinformation production from humans to LLMs. And we do need to call for more research and collective efforts on combating LLM-generated misinformation from stakeholders in different backgrounds. Okay, I will quickly talk about future research. So for future research, the first major line is how we can use LLMs for combating misinformation. Okay, there are several tasks we can do, including we can develop more trustworthy misinformation detection and how we can harness the multilingual and multimodal LLMs to detect misinformation and even go beyond the detection and use LLMs for intervention and attribution. And more importantly, how humans can collaborate with LLMs together to identify misinformation. And second line of research is how we can combat LLM-generated misinformation, which is a relatively new research area. For example, how we can alleviate a hallucination of LLMs, which is the major topic of today's summit, and how we can improve the safety of LLMs, right? Make it more, reliable to these jailbreaking attacks, for example, and how we can detect LLM-generated misinformation more effectively, and how interdisciplinary research from different backgrounds can do this together. So we do have this initiative, and you can scan this URL, and then we have a lot of resources out there. Okay, so lastly, these slides demonstrate our recent work and materials, including datasets, book surveys, and so on and so forth on the topic of misinformation. And thank you so much, and looking forward to the discussion. Thank you.
Thank you, Kai. A great discussion, and it's a very timely topic, I think, and very important these days, I think, more than ever. So I had, there's a question from audience here asking, when your system detects a misinformation in a query, in like in a statement, is it because there is a misinformation, because there's not a source in the like a knowledge oracle says it is not, or because composition of different parts basically tells you that this is not a correct information?
Right. So if I understand the question correctly, how we can decide whether the claim is correct or not. It's more basically, it's more based on the subset of the claims or an overall claims, right?
Yes.
Okay. Yeah. So essentially, when we design the ground truth of the claims, we rely on the fact checkers evaluation on whether this piece of news or this piece of document is true or not. But in many cases, that is true that it may be a mix of true and false if you look at more fine-grained information. So then in this case, we mainly look at the major claim that can be derived from this content. For example, the title or the major claim, and then we based on that to justify whether it is true or false. Yeah.
Yeah. So I have one time for just one quick question, if I answer. So. Regarding the fact-checking part, how do you know what type of oracle of knowledge like you need to refer to and ask about the correctness of any statement? In general, for any specific benchmark, probably it's clear, but in a general use case, how do you want to do this?
Right. Yeah, I think this is a great question. And in the paper I talked about earlier, essentially we assume that the information from Wikipedia or Google can be a proxy of the trusted sources. There's no 100% trusted sources that we can rely on in many cases. But in that case, because our data sets is from Wikipedia and the ground truth is collected from Wikipedia, so in the data set we use Wikipedia as kind of proxy of the external sources. And we do admit that this is not perfect because we cannot really 100% trust, but we present an idea of using external sources, if we have any, to better enhance the knowledge of existing LLMs. And this kind of knowledge grounding idea does help. Yeah.
Thank you. We can discuss more in the roundtable. Thank you so much, Kai. And now it's time for our next presenter, Dr. Danqi Chen from Princeton University. Danqi is assistant professor of computer science at Princeton, and the topic of her talk is enabling large language models to generate text with citations. Thanks, Danqi, for accepting our invitation for this summit, and please start. Your screen is not full. Your presentation is not full screen. Maybe you can.
Let me see. Does this work?
Still, we have the seat. Okay, great. Now it's great. Please.
Okay, good. Okay. Thanks, Ali, and thanks for having me in this event. Today, I'm excited to talk about how to make large language models generate text with citations. So in this talk, I will focus on one recent paper that comes out from my lab with the same title as this talk, Enabling Large Language Models to Generate Text with Citations. So this work was also presented at EMLP 2023 in December. And this work was done by my PhD students, Tianyu Gao, and also grad students Howard Yan and Jiatong Yu. So we also have a name for this project. So we call this project ALC. So ALC stands for Automatic Large Language Models Citation Evaluation. And ALC is also the Latin word for elk. So apparently elk is also another big, cute animal like many of our large language models today. So if you're interested in learning more about our project, feel free to go to this GitHub page, Princeton LP ALC, so you can find out more information. So at the end of this talk, I would like to also highlight some of the big future directions and also some of our ongoing work in terms of how we can actually really make progress on this important problem, and how can we actually move forward in the future. So I assume that everyone is already very familiar with that large language models are becoming more and more important as effective information-seeking tools. Today, if we just ask a question like in Google or in search engine, such as what is better for a family with kids under 3 and a dog, Bryce Canyon or Arches National Parks? So instead of letting the search engine display like several web pages, large language models can already output like a long paragraph of text, which gives you a perfect answer. So what are the fundamental problems of using large language models as information-seeking tools? So this actually really is the key theme of this event. So we are already very familiar with. So the first problem is actually hallucination. So we are very aware of that large language models tend to generate a lot of factually incorrect information, and that sometimes they also output outdated text. And also another issue about this is large language models output have actually no supporting evidence. So this makes users very difficult to actually verify the output and also trust large language models output. So in this talk, I would argue that a major paradigm towards solving this problem is to let large language models generate text with citations. So I'll give a more formal definition in the next few slides. But as a figure, you can see from the figure on the right. So instead of just let the model generate like the text, the output is also tagged with kind of inline citations that actually link to some trustworthy like evidence text. So what are the advantages for doing this? So very clearly, if the large language models output have this kind of citations, they actually become very easy to verify. And another potential advantage is if the output can be actually faithful to the citations, they can also have the potential to improve the correctness of the final answer. And this is actually not a new paradigm. There have been already a lot of explorations in this space. So people probably have already seen a lot of commercial systems trying to actually adopt this paradigm to generate text with citations, including Bing Chat, Perplexity.ai, and UChat. As an example, you can see from this slide. So the output also contains a lot of citations, and each of these citations corresponds to one URL page that comes from the search engine or from the internet. And there has been also some closed resource research efforts trying to actually tackle this problem. For example, there is this project called WebGPT that comes from OpenAI 2 years ago. So all of this existing work, they try to build on top of the commercial search engines, such as like Microsoft Bing or Google. And they also build on the closed source models, such as like GPT models. So what are the problems? I would argue that there are several key challenges here. So the first challenge is all these kind of existing works, they actually adopt human evaluation to actually really compare the different models and the systems. And there is such a very nice paper from Stanford. They actually did a very careful and a thorough human evaluation in terms of evaluating this kind of commercial search systems, they call generative search engines. And another issue of this line of research is that it's actually very difficult because they actually depend on the commercial search engines and the closed source models. It becomes very difficult to reproduce and compare the different modeling approaches. And I also want to note that all these works actually consider using the web pages or URLs as a unit of citations, which I also think is actually a very important design choice. So the key motivation of our work is that given this research problem is so important, so how can we actually formulate this problem and actually really measure progress on this important research problem? So this is actually the key motivation of our work, ALK. Again, ALK stands for Automatic Large Language Model Citation Evaluation. So let me first talk about the problem set of ALK. So ALK first assumes, so it's a benchmark. So it first assumes a question, natural language question. In this example, when did the US break away from England? And it also assumes a large retrieval corpus, as you can see from this figure. And the ALK actually requires us to build large language model citation system, which is an end-to-end system, which include first, the system needs to retrieve passages from the retrieval corpus. And then the system needs to generate like a coherent and long text responses that correspond to the question. Finally, the system also needs to cite the evidence passages, the supporting passages, as you can see from this image. So why is ALK actually unique? So in the next couple of slides, I would like to tell you more about ALK. That first, ALK actually features and collects a diverse set of the natural language questions and also the retrieval corpus. And the more important feature of ALK is that ALK also supports automatic evaluation metrics. So we actually put a lot of effort into developing automatic evaluation metrics, which measures 3 different dimensions of the large language model's output, including fluency, correctness, and also the citation quality. So we also explored a lot of the modeling strategies with the state-of-the-art large language models. We actually showed that even with the best large language models today, like GPT-4, there's still a very large room for improvement. So this problem is far from solved. So definitely, I encourage people to actually work on this really important problem. Okay, so next, I would like to give a little bit more formal formulation of this problem. So the problem setup is, let's say, given a question Q and a corpus of passages D. So the corpus, retrieval corpus could be pretty large. And we require the system to return output S with n individual statements. So here, each sentence can be viewed as a statement. And we require the system to output the n different statements. And each statement can actually be used to can actually cite a subset of passages. So here we actually allow multiple citations to actually support each individual statement. And then we just simply use the square brackets as the citation formats. And then finally, an important design choice here is we'll assume that each passage in this retrieval corpus is a 100 single word passage following the previous work in open domain question answering. So why do we care about this? So there are two arguments here. The first argument is if the retrieved evidence is only 100 words long, so actually much easier to verify compared to like web documents. Second, we all know that large language models today are still bounded by the context windows. So if we only consider 100-word passages, we can actually possibly fit more context in the context window of large language models. Okay, so next, let me describe the data sets that we actually consider in the ELK benchmark. So we actually put a lot of effort into thinking about, okay, how should we actually measure the progress and what would be actually the natural question answering data set that we should use in this benchmark. So we actually selected from a very large pool of question answering data sets with the following desired properties. So the first, we only care about the factual questions here. Because if we care about factual questions, that makes the citations actually more natural choices, and actually also really important to use citations to fact check the questions. The second, we care about the long form answers. So this is actually very different from the most of the prior work in open domain question answering, that most of the answers are just pretty simple and short that consists only of a few English words. And the third is that we actually care about the large language models output to actually be required to synthesize information from the multiple sources. So that means that one citation is actually not enough. So we actually really need the model to actually cite from like multiple different evidence to synthesize information to get the final output. So here is a table summarizing basically the three different subsets of the data set we used in the ELK benchmark. So I will go over and show you more examples in the next few slides. But as you see that we actually picked three data sets, ASQA, Campery, and ELI5 in the ELK benchmark. And the retrieval corpus could be actually also very different. So range from the Wikipedia, English Wikipedia passages, which consists of like 21 million passages following the previous work in open domain question answering. But we also consider much larger retrieval corpus from a common crawl, which consists of almost 900 million passages. And the question types are also very different. So some of the questions are ambiguous factoid questions, and some questions are more like list type questions, and some questions are like more like why and how type of questions. So let me show you more examples from each subset of the ELK benchmark. So the first data set we chose is called ASQA. Again, the question is a factoid question. Actually, this is a subset of questions from the natural questions data set, which is actually collected from the user queries from the Google search engine. But one important thing of these questions is that these questions are generally very ambiguous. So there isn't a single answer to these questions. So you actually really need to consider many different conditions so that that correspond to the different possible answers to this question. And the corpus is actually based on the English Wikipedia. So here's one example. So the question is, when did the US break away from England? And the output is actually consists of multiple possible answers conditioned on different scenarios. So the final answer is the US declared independence on July 2nd, 1776, and they need to cite like two evidences. And then it mentions the Treaty of Paris was later signed on September 3rd, 1783, which is actually another interpretation of the question, and they need to cite another source document. Here's another type of question in the ELK benchmark called Campery. So the question type is still factoid questions that actually requires output like the list type answers. And the corpus is still based on Wikipedia. So one example here is which films have Gong Li as a member of their cast. So as you can see, the output actually really needs to give a list of the answers, a list of films in this case, that actually lists a bunch of the films that Gong Li has been actually acted in these films. And they also come from the different evidence sources. And the third subset of this data set is actually a very famous data set called ELI5, the long form question answering data set. So this question is actually collected from the Reddit forum, like explain to me, like if I am 5. And most of these questions are like a why and a how questions. And we consider a much bigger retrieval corpus in this case just for the retrieval purpose. So this is one example. How do student loans affect getting a mortgage? And the answer is actually pretty long and actually really complicated. So it needs to give you the answer like student loans can affect the debt to income ratio site, and which is the key factor in determining the amount that blah, 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 and the site. So instead of like listing a bunch of the entities, so for this subset, only the reference loan answer is actually provided in this subset. Okay, so the next, I'm going to tell you more about how we actually developed automatic evaluation metrics for this ELK benchmark. So we care about 3 dimensions, as I mentioned before: fluency, correctness, and the citation quality. So fluency measures whether the generated text is coherent and fluent or not. And the correctness measures whether the large language model's output, the answer, is accurate and also covers different aspects of interest or not. And finally, the citation quality measures whether the answer is actually well supported by the cited passages, and also no irrelevant passages are cited. So I want to emphasize here that, so in this paper, we argue strongly that the 3 matrices and the 3 dimensions together can contribute to a robust evaluation. If we build a large language model citation system which only score high in 1 or 2 of these metrics, they are actually not sufficient for building a good system. Okay, so next I will give you some idea about how we actually develop these automatic evaluation metrics. So fluency is actually very straightforward. We just adopt the MORPH scores from this New York 2021 paper. And for the correctness measurements, we actually designed the data set specific strategies for the evaluation. So we have 3 different data sets. So we actually use the different strategies to evaluate the correctness. So I want to note that even evaluating the correctness of long form answer is actually still a pretty challenging problem today. So I encourage you to check out the paper for more details. So here, basically, like the correctness measures for the comparison subset and also ELI5 ELI5 subset. So we actually need to measure the both precision and recall in terms of the correctness. Okay, so finally, probably also the more interesting and the most important metric is actually this citation quality metric. So we actually need to develop automatic measures to actually measure both citation recall and the citation precision. And the way we do this is to actually leverage a state-of-the-art natural language inference model to consider recall and precision. So citation recall here means that whether the output is actually fully supported by the cited passages. So basically, by the way that we define the recall is that if there is at least 1 citation, if the natural language inference model tells us that the concatenations of all the citations fully support this statement, then we say that, okay, this output is fully supported by the cited passages. So next is citation precision. Citation precision measures whether all the cited passages are actually relevant and whether there is any irrelevant citation or not. So this is actually measured at the citation level. So we define the citation is relevant or not irrelevant. So based on if it's irrelevant, if this citation alone does not support the statement, but removing this citation actually does not affect the other citations to support this claim. So I encourage you to check out the paper for more details. We actually have a lot of careful design in actually designing these 2 different metrics for citation recall and citation precision. And as we actually show that state-of-the-art NLI model, true model, can actually do a very good job in measuring these 2 aspects. Okay, let's coming back to the three metrics together. Again, I emphasize that the three metrics together actually contribute to a robust evaluation. So we actually, in the paper, we show that if we just adopt some simple heuristics, like citing the top one passage, it can get a very high scores in some 1 or 2 dimensions, but it can be actually killed by some other dimensions. And another important thing I want to emphasize is that we also demonstrate very strong correlation between the human evaluation and our automatic evaluation metrics. That's why we believe this benchmark can provide a reliable and a robust automatic evaluation. Okay, so in the last part of this talk, I would like to talk more about how we can actually really build such large language model citation systems. And we actually explored many different strategies in the paper, but they can basically categorized into 3 different components. So the first component is actually the retrieval component. So we need to think about how we can actually retrieve the relevant passages from the large retrieval corpus. So in this work, we only consider off-the-shelf retrievals like DPR, GTR. And the second component is we actually need to figure out how to make large language models to interact with the retrieval, to actually better synthesize information from the retrieved passages to actually give you the better output. And we also developed some post hoc editing techniques to actually edit large language models outputs. So which include like some techniques like re-ranking or some post hoc citations, which basically just try to add citations after the large language models output based on some similarity scores. So I'm not sure if this kind of post hoc editing techniques are still very, very fundamental, but in the experiment, we show that they're still very, very important in the final performance. So really the key research question here we want to ask is how can we actually teach large language models to interact with the retrieval and also to synthesize the information from the different sources and finally cite evidences. So let me just give you a little bit of flavor of the system that we actually eventually built. So this is actually a baseline system. We call it just a vanilla model. So the idea here is that we just give the system an instruction and the 2 in-context examples. And then we just simply prepend all the retrieved passages in the long context of the large language model. And then finally, we just ask questions and let the model directly output the text and also the citations. And then we also adopt a lot of some like really cute ideas from the recent work on large language model agents, such as self-ask or react, that we actually consider some interacting prompting strategies or trying to do the retrieval on the fly during the generation of the large language models outputs. So here we actually develop baselines that we try to search among the pre-retrieved passages during the generation. And then we define the 3 types of actions. So the model can actually either search from the retrieval corpus or choose to continue outputting the text, or choose to just terminate the output and give you the final answer. So I'll just quickly go over this animation. So basically, we show that given the instruction, and we allow the model to actually really interact with the retrieval in this interactive way. So you can do search and get a document and generate the output, and then remove the document from the context and continue to search and output, and then finally it actually finish the output and gives you the final answer. So finally, I would like to give you like an overview of the results and some key takeaway messages from the experiment we explored. But there are actually a lot of results in the paper that I encourage you to check out. Okay, so the messages, key takeaway messages from our experiments include: we found that the baseline model, the vanilla model, actually can achieve very strong performance. And we found that actually the post hoc re-ranking technique can actually boost the citation quality. So if you do the re-ranking, the citation performance is actually improved a lot. So this means that there is actually large room for improving the decoding strategies of such large language models outputs. And we also find the open source models still lag behind the closed source models such as ChatGPT and GPT-4. And we also find that we also tested with GPT-4 models. We find that because GPT-4 supports longer context, if we can fit in more passages, they actually can achieve like a better performance, especially if we compare like feeding 5 passages versus feeding 20 passages. Finally, this is a kind of surprising finding to us that we tried a lot of different interactive prompting strategies. We actually found that interactive prompting actually really doesn't improve performance on this benchmark. So that really means that we found that this technique still really struggle with searching, formulating the right queries and really searching the relevant passages from the corpora. So we actually think there's still very big room for improvement, especially given there's a lot of really exciting large language model agent search going on in this space. And we also did some analysis trying to understand the impact of retrieval on this benchmark. So the conclusions here is we found that even if we feed the models with the gold passages, the current models still struggle with generating the correct answers. So this really means that the model still struggles with synthesizing information from the different retrieval corpus. So there is still a lot of work that we actually need to do here. We also find that better retrieval, let's say if we compare DPR and GTR, better retrievals can actually lead to better performance. And finally, if we can fit more passages, this can actually potentially lead to actually better performance. So that also means that long context large language models can actually play a significant role in solving this problem. Okay, so I know I'm almost running out of time. So I have 2 more slides left, and I would like to talk more about why. I hope so far I already tell you, okay, why this is actually a really interesting problem to solve, and why ELK could actually provide a reliable benchmark. So next, I would like to talk about where I see the future research is going in this line of research direction. So I really think there are actually lots of exciting opportunities in building large language model systems to generate text with citations that are actually really centered around a lot of the core developments of the large language models today. So the first avenue for improvement is actually the stronger retrievals. So in the paper, we only explored using off-the-shelf retrievals. But in the future, how can we actually train retrievals in an end-to-end way to interact with the large language models? The second, so how can we actually make large language models really make use of the more retrieval context in an actually more effective way? As I mentioned, I believe that long context large language models, which is actually very, very heated field right now, could actually provide a promising direction to actually tackle more retrieval context. But I also think it's actually very important to actually teach large language models to actually leverage retrieved context in a better way. So we actually have a paper actually coming out hopefully next week. We actually show that there are actually a solution to actually better retrieve, leverage this retrieval context in a parallel way to actually enable better generations with citations. And now finally, I also want to say that our previous experiment actually shows that instruction-tuned models outperform the base large language models in solving such a task. So I actually see that there's a lot of promise in actually instruction tuning of large language models to actually help these models better tackle this problem of the citing evidences. So the question is really what kind of training data should we collect, and how should we actually instruction tune the current large language models? And another unsolved problem, as I mentioned, is that I still believe that there's a lot of things we can explore in terms of interactive prompting. So how can we actually let large language models to better interact with the retrieved context so that the model can synthesize the information from the different sources better to actually give the final output? So I'm pretty much done with my talk. So I really hope that ELK can actually serve as a reliable and also robust evaluation benchmark for these all very important and core research developments of large language models. Okay, so I would like to just wrap up my talk here, and I'm happy to take questions.
Thank you, Danqi. A great talk and very important topic, of course, especially for the industry as the retrieval augmented systems, RAG systems are very much in use, and citation is an important part here. One question, just a quick question we can discuss more in the roundtable. Is the citation systems in at least current systems are mostly post hoc, basically generating citation after the fact, or are they effectively being used to generate more factual results as well? Is there a loop? Is there an interaction involved?
Yeah, great question. Yeah, I probably went too fast here. So we actually explore the different strategies. So one strategy I mentioned here is the post hoc citation. So that means that we just let large language models to output text, and then we do the citation at the end. But we actually find this strategy actually doesn't work so well. They actually achieve pretty poor scores in the citation metrics. So the better solution is actually really trying to let models to generate text at the same time to cite the retrieved corpus, retrieve the evidences. So it could be either interactive, or we can actually put the retrieve evidence at the beginning and let the models to figure out what to cite.
Yeah,
but there's still a lot of things we can explore here.
Yeah. So I have other questions we can perhaps discuss in the roundtable. Thank you so much. So our last talk here today is given by Huan. So Huan is Associate Professor of Department of Computer Science at Ohio State University. And the topic of her talk is Say Correctly, See Wrongly, Hallucination in Large Multimodal Models. Thank you, Huan. Please start.
Thank you very much, Ale, for the introduction and the invitation. I changed my title a little bit, as you can see on the slides. And also many thanks to the speakers for their great talks. I feel my talk might be slightly different. I'm going to introduce our work on web agents, especially the hallucination and grounding issues of using multimodal large multimodal models for developing web agents. And I might also introduce something controversial about hallucination. So let's say, all right. So let's start with what is hallucination. Honestly, I have been struggling with the term, with what exactly it is. So a few weeks ago, Andrew Karpathy made an interesting and also controversial point on Twitter, now X, that hallucination is all LLMs do. They are dream machines. It's only when the dreams go into factually incorrect territory that we label it as hallucination. So to summarize, he thinks that hallucination is not a bug. It is the LLM's greatest feature. So while I don't necessarily agree to rebrand it as a feature, as it will cause a lot of confusion, but I do find that part of what he is saying is aligned with what neuroscientists think about our brain. So you might have known that there are several peculiar properties of human perception. Consider the image on the left side. You can immediately perceive the word editor and also the triangle, sphere, and the bar there. But they're not actually what our eyes actually see. For instance, you can see that a lot of the lines of this, the letters in this word are actually missing. So in other words, our mind actually automatically and also unconsciously fill in the missing details. So in the 19th century, there is a German scientist called Helmholtz. He proposed a theory to explain these peculiar properties, which is often referred to as perception by inference. So in simple terms, it means that you don't perceive what you actually see, but you perceive a simulated reality that you inferred from what you see. And this is very interesting. And in the 1990s, Hayton and his student proposed a proof of concept for this theory, which they call Helmholtz machine. So you can see a lot of similarity with the later autoencoder and also Boltzmann machine. But in general, this model has two modes. One is a recognition mode, and the other is a generative mode. And it learns to recognize things by generating their own data and comparing the generated data to the actual data. So this is sort of like the constrained generation, and it also is an early proof of concept for modern generative models. If you think about it, although modern generative models are like much more complex and powerful. So there's also much evidence that our neural cortex is implementing such a generative model, which can well explain the previous visual illusions or peculiar properties. And it could also explain why we humans can dream and imagine things. So to Kapathi's point, that the inference procedure of LLMs is a lot like the neural cortex operates under the generative mode without constraints. That is, quote unquote, hallucinate stuff under some prompts. So, anyway, you may or may not agree with the statement that, hallucinations all LLMs do, but to, make us on the same page about what I think, about the hallucination problem or when hallucination causes a problem. So let me clarify. So in this talk, I will refer to hallucination as a model's generation that is consistent with facts or the given context, such as image or a problem description. I think this is consistent with what Ale introduced earlier in other talks. But if you think about it, how does it differ from a general generation error? So to clarify, I think this question is task dependent. But example errors that I do not consider as a hallucination error currently include, for example, in the math reasoning task, if the agent misses a reasoning step, for example, forgets to apply a rule, forget to multiply a number, I don't consider it as a hallucination. Or in the recognition task, if it fails to understand the meaning of a term or object due to lack of knowledge, then I don't think it's, I would call it a hallucination. So this is more like if you ask a pupil to solve a college level geometry problem, they can probably recognize the numbers, lines in the figure, but they don't understand the deeper meaning of those things in this problem context. I refer to such problems as a sort of a layman level versus expert level perception. So with all this clarified, in this talk, I'm going to talk about our very, very recent work on generalist web agents, which we call Mind2Web and C-Act. And I will particularly mention some hallucination issues we observed using large multimodal models to develop such agents. Some heads up, I don't have good solutions yet. This is very actively ongoing. But I welcome collaboration with anyone, Cisco scientists or other, researchers to join the force and work together to solve the problems. So why do we care about generalist web agents? So first of all, in our paper, also accepted in Europe's 2023, we define generalist web agent as given any website and any task, the agent can understand the natural language description of the task and then come up with a sequence of actions that can be executed on the website to solve the task. Why do we care, right? The web has been hosting billions of websites. We are using the web every day, right? We almost do everything on the web. But also on the other hand, the internet and the websites are becoming increasingly more complex, and websites are providing more functionalities, and many times it's hard to find something or complete the task at hand. And this is especially true for people, who are less tech savvy or who are physically challenged. Even for us who are familiar with the technology, we oftentimes spend quite a few minutes to complete the tasks. So That's why we want to sort of build such a generalist web agent that can improve the accessibility of the web and also enhance people's productivity. What are the challenges in doing so, right? We can imagine there are many user tasks that are very diverse, complex, and require long horizon planning, which means you need a lot of steps to complete them. And also the real world websites are very complex, dynamic, and they are constantly changing. Moreover, we hope the agent could generalize to unseen websites or domains. Because you simply cannot collect training data from every single website. So that's why we developed this benchmark called Mind to Web, which consists of over 2,000 tasks from over 130 websites and also 31 domains. And compared with existing data sets, we focus on real-world websites with high-level task descriptions. Here is a data sample from this data set, which consists of a task description in natural language, a website that we can complete this task on. And also, we annotate each task with a sequence of actions. Each action consists of two things here. One is the target HTML element and also the operation. So for instance, given this task, the agent is expected to predict the target HTML element and also the operation on each web page, For example, here at step 5, the agent needs to, based on the description and also the web page layout, predict, okay, the target element is the search element here. And also what it needs to do is click on this search button. So the web page will get refreshed and then the new environment will arrive. And then based on that, the model will continue to make predictions until the task is completed. So this is sort of the setup here. And in this work, we also develop the first framework for building such a generalist web agent. This framework consists of two components. One is the ranking model and the ranking module, and the other is the prediction LLM module. So because here we are just utilizing HTML documents, which are very long, and we developed this ranking module so that we can get a top K candidate elements, HTML elements from this long document. And then we will use this top K list together with the task description and previous actions as the input to the prediction LM so that it will generate or predict the target element and the operation to take. So this is the overall framework. Here are the main results. Basically, from here, the main takeaway is that using GPT-4 as the prediction LM, using just 3 demonstration examples, we can get close results to those fully fine-tuned FLAN-T5 models. FLAN-T5 is the strong model we find in this setup. But all models are terrible. You can see there is only 2 to 7% success rate for the whole task here. I should mention that these experiments are conducted under offline evaluation setting, meaning that we only assume one golden action sequence. And if the agent makes a prediction that is different from the labeled action at a certain step, then this whole task will fail. So this is a very strict evaluation. And also it's a limitation because we cannot support online evaluation at that time. And this limitation will be addressed in our more recent work that I'm going to introduce. So lately, we have set size on large multimodal models or LLMs. Why? If we look at the HTML and the screenshot, right? Apparently, web page is designed for visual consumption, right? It's much easier, at least for humans, to understand the web page screenshot than looking at the HTML code. And on the model side, actually, if you look at the screenshot, it is much more token efficient than the HTML document, meaning that, for example, in this case, the screenshot will only take maybe a couple thousand visual tokens, while on the left side, the HTML document might take hundreds of thousands of textual tokens to process. So we want to try the potential of LLMs for web agents. So that's why we developed this CACT, which is a multimodal generalist web agent. I'm going to quickly show the demo here. We just released this 2 weeks ago. It's very easy to play. And what you are seeing here in this video is actually the agent interacting with live websites. So we released this online evaluation tool, and very easy to play. Feel free to check it out offline. So the idea is given an action here, given a task here, the model will generate, action, describe the next action, predict which elements on the web page to interact with, and then we'll use an existing tool called Playwright to execute the action, and then the web page will get refreshed and the model will continue to make prediction until the task is completed. Okay, I'll stop here. So we are also aware of the safety risks associated with such an agent. So at this point, we do all online human evaluation by monitoring every single steps of the model's prediction. And by default, the model will always ask a human for confirmation at this step. But in reality, once this agent is more robust in the future, we can sort of sort of lose the standard and maybe make it more automatic, autonomous. So how does the CACT work, right? It consists of 2 stages. One is called action description, and the other is action grounding. So in the action description, using this example, what it does is that given the web page at a certain step, you have a web page, right? A web page screenshot. Given this, the model is asked to generate a description of the next step. And we are using prompts, which is sort of like a chain of thought, and in which we ask the model to identify the current web page, analyze the previous actions, and also analyze the current screenshot details before generating a description of the next step in natural language. So in this example, find the faculty center page for Ohio State University. You can see actually the model makes a correct prediction here, which is to click on the link titled Buckeye Link Faculty Center under this section. By the way, this is actually a query I issued earlier this semester. I took a maternity leave last semester, and when I returned, I found that this page actually has got changed and got quite hidden. So it got me quite a few minutes to actually find the hidden link in this page. Usually it was pretty easy to find. But anyway, so the model surprised me a lot by doing this kind of reasoning and figure out the next action. However, since I emphasize that this is in natural language, we still need to ground this to the actual precise HTML element, like what to click and what to select, which button on this web page to select or to click. How do we do that? So we first develop a method which we call grounding via Oracle. The idea is we can ask humans to identify models' intended actions from the action description. Here, we conduct the online evaluation where basically the agent is interacting with the real websites, just like in real use case. So we find that the result is surprisingly good. We can see we get a 50% whole task success rate, which is very promising and exciting to us because you can imagine if we can continue to improve the automatic grounding methods and get them close to the Oracle grounding method, then the whole agent can soon cross this 50% whole task success rate milestone. However, in our current automatic grounding methods, we still find there is a large gap between the automatic grounding methods and those and this Oracle method. So there is still much room to further improve. We actually designed two automatic grounding methods. One is called grounding via textual choice. So the idea is very simple. Basically, remember the ranking module I mentioned earlier. From the ranking module, we can get a ranked list of HTML documents, HTML elements, and we just treat them as text. And then we, together with the action description generated in the previous stage, we give it to the model and ask the model to select one of the options here, so that the tool we use will pick this action and then sort of click on it or select the button and move to the next page. Another method we call grounding via image annotation. So the intuition is that okay, since image or screenshot is much easier to understand, why don't we convert these textual choices into, let's say, grounding box on the image, and so that each choice is has a grounding box outside it. This is much easier for humans to understand, actually, and we hoped that this method could outperform the textual choice methods. To our surprise, that this method does not work well, and we observe a lot of error types. One issue or major type of errors is hallucination. I will explain what it is in this context by showing two examples. So in this example, as you can see, the task is, as a Verizon user, finance a new blue iPhone 13 with 256 gigabytes along with monthly Apple Care. So in previous actions, actually the model has figured out the correct Apple configuration, as you can see at the left bottom here. And also it has correctly chosen yes to the question, do you currently have service with Verizon? So now the next action should be simply click on continue. In fact, interestingly, if you look at the GPT-4V's response, it could actually describe the action correctly. It does say to click on the the continue button. But more interestingly, if you look at the red part, it says that after reviewing the screenshot provided, and the continue button does indeed match one of the highlighted elements with the red bounding box, which is not true. And it doesn't label with the, is not labeled with the letter H as well. So we call this issue as a sort of the model is fabricating a grounding box and a label in this case. And in another example, you can see, again, this model can describe, the next action, like click on the sports filter. But after that, it hallucinates some stuff, like this sports filter is labeled with the letter O next to the red box, which is again not true because this model, this part is labeled as N. So these errors might be due to the basic layout, and also the bounding box might be too close to each other. But there are some fundamental differences between web pages and also the regular images as seen in some conventional benchmarks such as ImageNet. So here in web page, there are usually many elements, much more elements to interact with. And it's hard for the model to figure out which is which and correctly understand the meaning and connect them with the task description. Interestingly, we also observe similar issues in developing and evaluating models in our recent benchmark called MMMU, which is Multimodal Understanding and Reasoning Benchmark. Today, I won't be able to talk about this benchmark, but I hope you can check out the details there. Basically, it is a large benchmark for evaluation on college level problems. We have multiple domains and subjects. So for example, here we have a science problem with a description, multiple choices, and also some problem from tech and engineering, which require multiple steps of reasoning to figure out the solution. And there are different levels of difficulty. Okay, with all that, I'm going to summarize. So basically, here, I guess we all agree that hallucination and grounding is a big challenge for large language models and also large multimodal models. And there is still, a lot to do, apparently. We are still actively exploring more effective solutions to combat this challenge. So one direction we are exploring is to find ways to train better foundation models. And one concrete idea is to develop some synthetic data where we can leverage the pair between HTML document and the screenshot to develop some good, like simulated annotations to train better foundation models, at least in the web agents scenario, but maybe it could generalize beyond. And also we can develop a system which might have those kind of self-correction abilities through iterative procedure for generation verification. I think similar ideas have been mentioned in earlier talks as well. And also echoing my earlier point on layman level and expert level perception abilities, we may also want to enhance domain specific and up-to-date knowledge in the larger models to mitigate the hallucination issues. So I'll leave enough time for questions, and thank you very much for your attention.
Thank you, Juan. It was a great talk, and very actually thought-provoking and imaginative. Just the WebMind and this project for general basically an agent that can do everything for you in the web. It's very actually interesting and potentially useful. I have a couple of questions regarding this. So you mentioned the safety issues. That is definitely going to be an important part of this. But regarding the path that agent basically takes, in similar to many multi-agent scenario, you may have different paths towards solving the solution, even in the web page, basically. Do you consider the multiple paths towards that, and consider like tracking back to certain stages in the process, or is it just one path?
Wonderful. Settings, offline evaluation setting, and online setting. So in the online setting, basically what we do is we will monitor the agent to interact with the real websites. And in that case, we actually do consider multiple alternative paths to complete a task. So there, in the online evaluation setting, we have a human to make the judgment call whether this task is completed or not. But in the offline evaluation setting, due to, it's just simply hard to maintain or collect all the possible paths to complete the task. We have this offline evaluation setting, meaning that at each step, we assume the golden action is given in the previous step. And then based on that, can we make a prediction for the current step? But I think going forward, because we released this online evaluation tool, and people can do more on the using the online evaluation setting. And moreover, I would emphasize this tool can enable a lot of exciting research opportunities, because you can imagine now reinforcement learning, kind of ideas will be possible. And in fact, we are going to explore this in which the model could possibly self-learn and self-correct mistakes made in the previous steps as well. So yeah. Okay, I might add one sentence here. So basically, if you get a chance to, or any of you get a chance to play with the demo, you will see we allow human to intervene with the agent. In that case, we can provide some feedback for the agent, allowing the feedback the agent to go back to the previous step and then make a make another prediction and move forward, things like that.
We probably shouldn't use it for like sensitive banking and stuff like that.
Yeah, we're far from there yet, but yeah.
Okay, no, this is great. I'll look forward to playing with that tool and learning more about it. This is very exciting.
Feel free to send us any feedback. We really indeed welcome any kind of collaboration opportunities.
Thank you so much.
Thank you.
Thanks for the great talk. So I think now this concludes our 4 scheduled talks in our summit, and now it's time for a roundtable. I invite all participants. Yeah, thank you all for presenting your work. It was a great session. I really enjoyed all the talks, and I really appreciate you taking the time, given your busy schedule, to be here with us today. So I have a couple of questions lined up, but please feel free to engage and even start a new discussion depending on what you think is important to discuss here. So my first question is the obvious one. So how do you see the path forward in terms of hallucination and the reasoning capability of LLM, the factuality? Do you think that in a near future there will be like better, more capable models, like for example versions of GPT-5 that or some other models that can effectively resolve many of the current issues that we are dealing with hallucination? Or will it be always an ongoing problem, requires active basically mitigation and detection on our part, basically? Please feel free to jump in, anyone who wants to.
Yeah, so I like to start. I feel like this is definitely very challenging because what we learned, if there's anything we learned about ChatGPT, is the scaling, right? I think that surprised everybody that by doing scaling, you really can solve all of the grammatical issues. Because if you look back like 3 or 4 years ago, nobody in NLP believed that you would be able to generate such high quality output. So scaling solved some sort of like grammatical issues. But on the other hand, I think people still running into issues because in the training, like I said, it's just predicting the next token. But you know, in the generation time, you do need to make sure it is you know, faithful, right, to the underlying facts. So it's very difficult. I think today's panel is really wonderful that we put together all this expertise in looking at hallucination, misinformation, adding citation, using agents. I feel like this is all really wonderful avenues of research, because my understanding is that you can't really like use the existing paradigm to solve the hallucination issue. So I think it would be future would be collaborative AI, that we would need all these different tools, all these different approaches to deal with the you know, the challenges.
I agree with what William was saying, and I would like to add that from my point of view, I think both parts will be necessary. That is enhancing the abilities of foundation models and also having some mitigation strategies. So I'll use the large multimodal model as an example. I think in our experience, the basic visual, the foundation visual encoders are still very weak in making, you know, a lot of rudimentary perception errors. So I think in future work, people can still enhance those foundation models. But as I mentioned in the first part of my talk, I actually think unless there is a fundamental change in the generative model, how it is trained and what in terms of the model architecture or things like that, I feel hallucination will always be there. I think it is more possible to just to develop all kinds of effective mitigation strategies to alleviate the problem. So yeah, those will be my 2 cents.
I can go next. So I have been a strong advocate for this new paradigm of retrieval augmented language models or retrieval-based language models. So basically, I believe that we cannot really rely on the parametric knowledge or the parameters of the large language models to store all the long tail knowledge. So the solution must be, we have to put those information in our retrieval data store. But the bigger question for me is whether we should actually really build a retrieval component as like a natural built-in component and train this kind of retrieval augmented models from the scratch, for example, as an alternative to large language models. Or we should actually view the retrieval as an external component that we can actually build this kind of agents type of work to actually interact large language models with the retrieval. That's a big question for me now. And just in case people are interested, we actually gave a ACO 2023 tutorial on this topic. So if people want to learn more about the recent research.
Right. I agree with all the panelists. I think I may provide a little bit more from the misinformation perspective. I think in the past, people are working on misinformation basically focused on human written misinformation. But now in the age of LLMs, we're actually dealing with the alignment of human and machine or LLMs because it's basically a 2x2 matrix, right? Like in the previous research, people are working on how machine can better detect human written misinformation. But now we have to deal with this new type of misinformation that can be intentionally or unintentionally generated. And in the talk, I present one attempt to try to use external sources to better enhance the knowledge grounded answers to better combat misinformation. But I think there are many more research needs to be done to enhance the factuality of the LLM's output. Yeah.
Yeah, that makes a lot of sense. Thank you all. So this need for a retrieval system also point out another issue is that we need some external oracle of knowledge to make these models more factual. So what will be the authority? So are we going to always rely on projects like Wikipedia and they're basically this form of community-based knowledge sources, which are great, I agree, but there are problems with the reliability of themselves, also problems with the fact that retrieval is really not a precise, basically, a skill right now. And as Danqi mentioned in her talk, that there are a lot of issues with the current retrieval systems. So what would be like a better path towards building a knowledge oracle that makes these models more factual? Is there any project that you are aware of that can be basically a starting point for this, or are we always going to rely on like Wikipedia and Google search?
Yeah. So I think that's a wonderful question, and my understanding is that for the generative AI systems, you want it to be compositional, right? You don't want it just to copy your training data and give it to you. So you want compositionality, but there's a trade-off between compositionality and hallucination, because when it starts to make up things, when it starts to compose, all these different tags, then there's this, hallucination issue. So unless you don't want any compositionality, I think hallucination is still gonna be there. So why is the external, fact-checking or external tools like retrieval useful? I think, that's what we have to do because, the model itself, I think it could be biased towards its own output. So that's why in many cases that, you cannot, let's take soccer, for example, you can't really be the referee and player at the same time. So you have to get some external information to really help you to make better judgment. So I think, all these different paradigms really makes a lot of sense because we need new information, right, to verify the existing information.
But if there is no authority for the knowledge oracle, there can be always multiple different or even contradictory sources of information. So how are we supposed to tackle that problem?
Yeah, so we wrote a paper called Contra QA a few years ago, and that was actually trying to look at the case that how do you do QA under contradicting context. So that's extremely difficult. We showed that accuracy is really low, even for some of the state-of-the-art system, because the contexts are contradictory. So I think to solve that problem, we need metadata. We need additional information. For example, we know this particular article comes from AP. There's another article comes from an unverified source. So sometimes using this, additional metadata, trustworthiness information in addition to text, that would really be helpful for this kind of problems.
I believe another fundamental problem is, let's say if you have a retrieval and the current paradigm is just simply put the retrieval passages or documents in the context of large language models. And the model, so there could be some irrelevant context there, and some context could be contradictory with each other. But the large language models, even either the base model or the instruction to the models, they're actually not taught to really discern the irrelevant context or really detect the contradictions yet. So I actually believe this, we can do something in terms of instruction tuning to actually better solve this problem. Yeah.
Yeah, can we rely on the common sense knowledge of these language models to, in the presence of like a contradiction or contradictory basically facts, find the relevant, more reliable citation of information?
I think the model probably already have that knowledge information. But the question is, if we just simply prepend this context, the model probably would not be able to redo this. So probably like how to prompt these models could be still very important. Yeah.
Makes sense.
Yeah, I think it really depends on the applications we're looking at to answer whether common sense really can satisfy the requirement. For example, in traditional fact checking, you're mostly looking at the knowledge graph or knowledge base that are already there. But now, misinformation, fake news, they are often timely information, and the data may not be there in the knowledge base that we can rely on. So it's really, I think I agree with other speakers mentioning we need more resources and we need more sources of knowledge input to make better judgment in this case. Yeah.
To go back to the point, whether we can rely on the model to discern conflicting information, I'm not comfortable to do that at this point. I believe there is a lot of work. So for example, Ali, you presented this example debating with not debating, but presenting some confusing information to ChatGPT, saying how many letters say are there in this word, and it will yield to you, right? Guess we also have a related work which we titled with can ChatGPT defend its belief in truth, and actually we show a lot of limitations in its reasoning abilities. But anyway, so I feel there is a lot of work in it. It's a very good idea, but it seems like there is still a lot of work in order for make the LLMs to do that part. And the second is in terms of other information, I think this is also maybe task dependent or domain specific information could also help there. So for example, you want to build an assistant for Cisco that can help answer user questions. Of course, you have a lot of internal documents or internal database you want to use. So in that sense, how do you maybe combine with Wikipedia kind of like a knowledge source and your internal knowledge source to make the LLM more grounded to those corpora? So that might also be an interesting direction to explore.
Absolutely. Thank you. Thank you. Makes a lot of sense. So let's change the topic a little bit. So there is a lot of discussions about the quality of data for training language models. How do you see the role of factuality and correctness of training data for LLMs? There's I have seen some work that state that using more factual and filtered data for training LLM has benefits in terms of at least performance on some benchmark. But there is another argument that this basically is that can introduce some new problems in terms of robustness of these models, in terms of contradictory information and things like that. So do you have any insight on this problem?
Yeah, so this is super exciting because I think the high quality training data is one of the best kept secrets of large language models. The reason is because let's think about, writing email, right? It's a very simple task. If you just scrape the web, how many emails you're gonna get, right? So if you just look at, the open source email data sets, it's just the Enron data set from 20 years ago, and it's barely usable, it's very small. So I really strongly hypothesize that if you really want to build some of the strong capabilities, for example, writing emails, you have to purchase proprietary data that really are high quality, that you're able to generate high quality result. I believe this is what OpenAI has been doing, that I think is open knowledge that many of this, people who are training large language models, the cost of acquiring licensed data or acquiring open source data sets, this is one of their biggest effort. And I think for the teams that has been doing really well, my understanding is that there has been a lot of effort. For example, OpenAI has been working with Scale.ai and many different companies to collect training data, whether it's for pre-training or whether it's for RLHF. This is going to cost a lot of money, but it is worth the investment. On the other hand, we also see some other academic collaborations, for example, the Bloom, and many other large language model that is out there. I think there's a challenge is that sometimes nobody wants to clean the data set. Everybody wants to train the large language model. So that becomes a big challenge, I think, for academia to do this, because everybody wants to do the fun part. So I think my point is just to emphasize how critical it is to bring high quality data for training large language model.
Thank you.
Okay, I agree with William. It's funny that I'm actually currently working on a project for data selection for deadlines of 2 days from now. Okay, so we actually have experiments. So we try to actually select data based on different criteria. And one category is actually to select data based on the factual information, the trivial information that you just asked about. So the answer is, it really depends on what we care about downstream use. If we just care about in-context learning results for like general NLP tasks, selecting factual data might be not that helpful as like a high quality pre-training data compared to let's select data with more high educational values. But if you care about more like this kind of knowledge intensive task as a downstream task, I would say this could be more useful. But I still believe that we should actually use more external knowledge to solve these tasks.
That's actually a great point here. Is if you want a model to be capable of detecting like false information and or contradictory information and things like that, the model is beneficial for a model to see a lot of instances of these type of text. And if we filter everything out, then perhaps its performance on benchmarks will improve, but it may suffer from some other new skills that is required. That's interesting. Any other comments on this topic?
Yeah, I mean, I would probably think of this question from the life cycle of training a large language models, but your question is more about the training data, which is like the pre-stage of training LLMs, which, to be honest, from academic point of view, we don't have much control, and because we don't have access to those data. We cannot choose and which data to purchase, which data to use. But if you think about the life cycle, actually, we can do more research on the data generated by LLMs and try to figure out how we can better use this data in a very legal way or in a more responsible way, right? For example, can we use this data to go back to train large language models? Is that good or bad? And I think we have more work to do on this side as academia research.
Yeah, to echo the point that although we don't have data access to the pre-training data, a lot of cases we are adapting those foundation models to those domain-specific scenarios. But for example, through building instruction tuning data set to tune a model that can follow instructions to do domain-specific tasks. So in our recent work, which we are going to release hopefully next week as well, we are building a sort of instruction tuning model for the chemistry domain, where we find that the data quality for instruction tuning is also very important, and you might get a very different results by sort of refining the data quality there. Just to add a data point, in the instruction tuning phase, we can also pay attention to the data quality there.
So is there any effective way of fixing this issue after the fact? So like in a fine-tuning way, in an efficient manner, we can fix some of the problems and the misconceptions that are generated by these language models. Is there a real path towards that, or that's basically going to be very expensive, and we may basically still rely on detection and mitigation strategies always?
Personally, I feel we will still rely on the mitigation strategies, but the results from the foundation model part or the LLM itself part could be much improved by a lot. But that said, we still need to rely on other strategies.
That makes sense. So one question we have from the audience here with regards to explainability, I also think that it relates to the talk Danqi presented. So what's the role of explanation in terms of LLM generation? Do we always need to provide explanation, and do we need to go even beyond this black box explanation? Do we need to have more internal representation on anything of that level? There were some. So in the old days that it's not old really. In the computer vision, we were looking at the internal basically layers of a network and to help with the explanation and stuff like that. But these days for language models, most of the works are focusing on the black box aspect. So do you have any idea where the explanation at the level of the internal network layers can be helpful?
I can try to give answers if I understand the question correctly. So first, I think interpretability as a research field definitely has a very long way to go. A lot of people are excited about, for example, mechanistic interpretability, but this type of research still work on a relatively small model in a pretty limited domains. But the large language models, they have hundreds of billions of parameters. I really think the scalability, how to scale up this kind of interpretability approaches to make things really interpretable is a very, very difficult problem right now. But there are also a lot of research right now trying to prompt large language models to generate explanations to by themselves. There are definitely a lot of things that we can work in that space. And just to circle back to my talk, I guess my point is more about can we add attribution instead of the explanation? So can we actually really fact check the generated output by comparing against reliable information sources?
That makes sense. Thank you. So one more question here is regarding the scalability of approaches. So many techniques for mitigation, for detection and mitigation strategies are expensive, require multiple paths in generation and a lot of agents involved. So how do you see this basically playing out in real in the industry and in real use cases? What are the concern and what do you think are going to be the solutions here? Any volunteer for this question? But it seems that we don't have any answer to this problem. Perhaps it's an unresolved issue. So we have only 5 minutes left. So I will invite every of our esteemed speakers to just mention some of the potentially interesting direction in the future research on factuality on LLM. What do you think that is going to be the most relevant and important topic there in the next few years? Please, William, you can start, please.
Okay, thank you very much, Ali. I feel like, there are two things I mentioned in the talk would be very relevant. One is to fundamentally understand the science of large language model that help us to understand why there's hallucination, right? And then if we do not understand why there's hallucination, I think it will be very challenging to solve the problem. So right now, there's a huge gap between empirical results and also the theory. And I feel like we need a little bit more work trying to understand the issue, right? The root cause of this hallucination. So the first part, I think, would be trying to understand the science of LLM that will help us with the algorithms and the tools that we design. The second part, I think we need to understand a little bit better is, tool use, right? So for example, what are the different tools, right, that are needed, right, to solve the problem? And sometimes API calls are also very different from the actual tool use, because the idea of LLM agent and the tool use, I think, is very broad. So Huan does this very impressive work on web agents. But in addition to web agents, there's actually robotics, right? There are actually problems that we need to solve to have LLMs to help us to cook, to help us to clean our house and all this different stuff. So that I think is possible, but that does not allow any hallucination, right? So if there's a hallucination, you want a robot, LLM robot, to pour you a cup of tea, someone could be in trouble. So what I see is that this is a super exciting area to connect LLM with different areas in CS and outside of CS, but to have precise control of the action and outcome, I think we need a better understanding of the tool use and better developments in tool use to help us to do better in this area.
Thank you so much. Kai, can you go next?
Yeah, sure. So I think basically, based on my talk, I think we really need to build a more collective effort on understanding the misinformation in the age of LLMs. As I mentioned, in the past, people are mostly working on human written misinformation, but now we don't know much about this LLM generated misinformation right now. And what will happen in the future is still remain underexplored. So I think we first need to leverage the capacities of LLMs to better understand and identify traditional misinformation. On the other hand, we also need to really be serious about this new threat of LLM generated misinformation and how we can build more responsible and reliable machine learning models to deal with that. So I think that's really important and need a lot of future research.
Yeah, that's true. We are entering a new uncharted territory with the LLM, so we have to be very vigilant. Danqi, please.
Yeah, I feel I also already said this in my talk and also in the panel. So I'm very excited about the developments of the long context large language models and how to make these models better leverage context, additional context. I think there are a lot of open questions there. And another thing is how we can actually really train better retrievals and also integrate retrievals into large language models in a more organic way. I think there are a lot of things there, that I'm most excited about.
Thank you so much. Huan?
Yes, thanks, Ali. I want to circle back to some points I mentioned at the end of my talk. I agree with all these great ideas. I think we should, I really hope we have more hands to explore all of them. But personally, I'm very excited to explore the potential of synthetic data. So I think we might all read the recent paper about alpha geometry, which design the model to, solve really difficult, Olympiad level geometry problems from DeepMind. I think it also sort of echoes William's points of using, symbolic solvers to help the LM, or at least they can play together in synergy to solve the complex problems. And another point is that they actually explore a lot of synthetic data to train the system. I want to mention that the synthetic data are not just developed to train the model, but also we can design some synthetic benchmark to understand the model behavior, to probe, what's going on and what might be wrong in, the model's results. The second thing is, I strongly believe the LM itself won't, just get rid of hallucination problem by itself. I feel we are building a more complex system with multiple modules, where the different modules can complement each other or correct each other, things like that. So perhaps there should be some kind of a multi-agent system where they can work together and in a sort of iterative procedure to verify each other's statement, things like that.
Great, thank you. That was a great conclusion to this wonderful event. I thank you all again for participating here. I really enjoyed all the talks, and I hope that our audience also enjoyed this presentation and discussion. Thank you all for joining us today. Thank you.
Thank you very much.
Thank you.
Thank you.